with your face showing in bold.
Well, if I share my screen, you'll see my screen and my face, won't you?
We'll see your thumbnail.
Right, that's better. I will do that. Let's see. Is that all right?
That's good. Nice and full screen and so forth.
I'll get a pointer too while I'm at it.
Yeah, do that. Okay, it's 12:35. So I'll start with a brief introduction of Mark, and then we can begin. So thankfully, Mark has agreed to talk to us about alloy-based negative electrode materials for metal-ion batteries, not just lithium-ion batteries. Mark did his bachelor's degree at Simon Fraser, his PhD here at Dell. I think he graduated in either 2000 or 2001. Then he did a postdoc at Cornell with Frank DeSalvo, who is a very skilled solid-state chemist. After that, Mark went to 3M, where he worked in the battery materials group there for about 10 years, focusing mostly on silicon-based alloy negative electrode materials. And Mark's work during that time represents some of the best work ever done on alloy-based negatives in the world. Mark received 3 major awards while at 3M. Technical Circle of Excellence award is given to just a few researchers at 3M on a yearly basis, and he received a number of very high awards at 3M. So he came to Dell about 11 years ago. He's in the chemistry department, and it's unfortunate the way that Mark is working with Novonix and we work with Tesla, so it's unable for our groups to collaborate the way it would be really nice to do so, because we would learn so much more from one another. But anyway, it's our chance here now to learn from Mark, so I'll take it away.
Thank you, Jeff. I think you gave out the handouts for the slide. I did make a couple of changes this morning, nothing major, but you'll see a couple of slides have changed. So to get into it, let me first talk about graphite, because the whole idea about introducing alloy materials is to increase energy density beyond what you can do with graphite. And the point of this slide is just to state that that's really difficult, because graphite is really a good material. It's very hard to beat in volumetric energy density, and especially in cost. It has I think it's almost ideal characteristics for a negative electrode material. And having all these characteristics come together, high capacity, 2.5 times higher than the cathode, volumetric capacity matches the cathode almost exactly, so that the electrodes are about the same thickness, they're well paired. Has a very low average voltage, which is perfect for a negative electrode. It's not too low, otherwise you could get lithium plating. Kinetics are excellent, rate capability is excellent, irreversible capacity is quite low, thermal stability is good, cycle life's great, Coulombic efficiency is high. It's a pretty inert material, doesn't react with much. You can densify it. In fact, in some cases, you might add graphite to the cathode as a lubricant, a calendering lubricant, to improve density. And it's highly expensive, and you could just take it from the ground directly. So with characteristics like that, it's very difficult to improve upon. And we'll see if we can improve on it a little with alloy materials. I think the best theoretical improvement you can possibly make is something like 20% increase in energy density in the cell, but that's theoretical. And we'll see the reality might be a bit lower than that. So first of all, how do you go about making a higher energy density material than graphite? Well, the first thing to do is to look at the periodic table. And graphite is up here, of course, and you can make LiC6. And there are a lot of other elements that can react with lithium. And the other elements either form intermetallic compounds or alloys, or they form ionic or covalent compounds. And of course, you want the negative electrode to have low potential versus lithium metal. That means the bond strength to lithium should be low. And therefore, if it's forming strong bonds, the potential of these materials is going to be too high. You know, oxides and fluorides, those are cathodes. These metal elements that form alloys would be the ones that would be contenders for negative electrode. And these ones in between are neither good for positive electrodes or negative electrodes. They'd have a potential in between the anode and cathode. So these alloys are the ones, according to their potential, that you'd look for negative electrodes that might be able to enhance the energy density. And in a lot of papers, you see graphs like this, where you can calculate just from the phases that are formed from lithium in these elements, the known phases that are formed, the intermetallic compounds, you can calculate what the volumetric capacity is, or the gravimetric capacity. But really, these kinds of graphs don't tell you enough. You have to take into account the potential to get the full story. And for the negative electrode, that's a little bit more difficult than the positive electrode. Typically, in research papers, if you're working on cathode materials, you can state an energy density. And typically for cathodes, you calculate the energy density as the average lithiation voltage. That would be the discharge potential in a full cell. And then you multiply that by its specific capacity and density, and then you get an energy density in watt-hours per liter. And so by convention, for cathode, you can calculate energy density taking the negative electrode as being 0 volts. For the anode, you can't do that. If you take the average potential versus lithium, of course, you'll get a tiny number, hopefully, if the potential is low. And this energy density calculation would be meaningless if you did it in the same way as the cathode. And the reason is that, strictly speaking, you cannot calculate the energy density of a single electrode. It's not a defined quantity. So what you need to do instead is calculate the energy density for a cell, a whole cell. What's the cell going to be if you use this anode? And so Vincent Chevrier and I worked that out in a paper we published. We just built up a standard cell stack. So the separator and the anode, double-sided coated anode, another separator and a double-sided coated cathode. And this is sort of like a unit cell in a wound or a stacked lithium-ion cell. You can take this unit and just repeat to build up a cell. And then we calculate the energy density of this thing for some standard cathode with some standard porosity. And if you do that, you get an equation that looks like this for the energy density of the stack. Here in this equation, this Q tilde R minus is the volumetric reversible capacity of the negative electrode. And here, this is the average potential of the negative electrode versus graphite. And you could see by eye in this formula that this quantity of the energy density of the stack, the volumetric energy density of the stack, is much more sensitive to the average voltage of the negative electrode than its volumetric capacity. And of course, also its gravimetric capacity. So you can see why, going back to these slides, that really this doesn't tell, not even the full picture. It tells, doesn't say the most important information, which is related to the potential of the negative electrode, which has the greatest impact on the volumetric energy density of the cell. And we could plot the potential of these materials that form alloys with lithium, and you can see there's quite a variation. So you would expect that this potential could have a big impact in the energy density of a cell. And indeed it does. So if instead of plotting volumetric or specific capacity of these materials, you plot the stack energy density in watt-hours per liter, then you can see a different pattern forming. Silicon is no longer the material that has the is the largest, I guess, in this graph. In the previous graphs of volumetric and gravimetric energy capacity, silicon had the highest. Here it doesn't, because its potential is higher than silver and magnesium. So according to this graph, if you wanted to choose an element to give you the highest energy density cell, you would choose magnesium or silver. The problem with magnesium is the kinetics are extremely slow, and the voltage of magnesium is almost 0 volts. And so lithium plating is quite easy with magnesium. And so it's not, well, not yet. Nobody's made it in a practical form that you could use it. And obviously silver might have a problem because its cost is high. And so you're left with these elements, silicon, tin, and lead. Lead is a little bit too toxic to use, so people don't use that. And so then there's silicon and tin. Zinc and aluminum, you would think might be possible, but there's another problem with them that, if I remember, I'll get back to later on in the presentation. And if I don't, somebody maybe can remind me to say why these materials, although their energy density looks good, why they might not be practical for use in a lithium-ion cell. At any rate, the focus has been on silicon and tin, and especially silicon. And the reason why silicon is one reason why silicon is preferred over tin is, again, cost. And you can calculate cost. A useful way to calculate cost is how much money you have to pay per amp hour in a cell. And these materials have, close enough potentials that we can work with amp hours instead of watt hours here, especially with the large differences involved. And you can see if you calculate capacity, or I guess capacity normalized cost, silicon is by far the most economical negative electrode material, even more so than graphite. It's only 0.06 cents per amp hour, as opposed to graphite, which is almost 1.5 cents per amp hour. And both are much cheaper than tin. So this is the main reason we focus on silicon. Another reason we focus on silicon is because of processing, ease of processing. It's much easier to make, to work with silicon to make the kind of composite electrodes you need to make them cycle well. It's much more difficult to work with tin, mostly because it's very ductile and has a low melting point.
Can I ask a question here?
Yep.
So this is quite a compelling table. And are people knowledgeable enough from the point of view of people purchasing these materials to realize that the cost of silicon-containing materials could be, up to virtually $100 a kilogram and still be at the same cost per amp hour compared to graphite?
I just wrote a book chapter for Kongshu on alloys that's coming out. And the topic of the chapter is exactly that. And I think in that book chapter, I use this capacity normalized cost to estimate the cost of silicon alloys, and SiO. And even at the most expensive estimates of how much SiO costs, it still works out to about the same cost as graphite on this basis.
And what was your most expensive estimate for the cost of SiO, out of curiosity?
I can't remember. It came from a paper from Doron Orbach. He wrote a review which had a ridiculously high price of SiO. I could tell you later what it was. I can't remember the number. But I couldn't believe, I mean, it was way higher than anybody else. But still, even at that high price, it still worked out to be equivalent with graphite.
That's crazy. All right, thank you.
Yeah. So the, why don't we just replace graphite with silicon? And well, it's hard. And first thing you notice is the chemistry with lithium is very different. If you lithiate graphite, there's lots of room between the layers that are widely separated. They're only held together by weak van der Waals forces. And the lithium can go between the graphite layers without changing the structure or expanding the volume very much. Silicon and these other elements, silicon has a diamond structure. There's no room really for anything else. And if you add lithium, it has to break bonds and change the structure to lithiate silicon. And what you get at full lithiation at room temperature is lithium-15 silicon 4. This structure represents the closest packed arrangement of spheres of different sizes with this stoichiometry. And you could see that now you have no silicon-silicon bonds at all. In fact, you have something that looks like silicon in a sea of lithium. And this is why silicon can, I think it's like 16 times as much lithium per host as graphite, because you can form structures like this. When you take lithium out of this structure at room temperature, the atoms don't have the thermal energy to reorganize to the diamond structure, and so you form amorphous silicon. And the volume change represented on this slide is about right. You get about a 300% volume expansion during lithiation, and during delithiation, it contracts down again, but amorphous silicon has a slightly higher volume than crystalline silicon. So you get these massive volume changes during lithiation and delithiation. The other interesting thing is how these materials lithiate in comparison to their thermodynamic phase diagram, the binary phase diagram of these metals versus lithium. And here I've superimposed some voltage curves of lithium inserting into tin from two different publications. One is by Bob Huggins, who did some pioneering work, lots of pioneering work in this area at high temperatures. And then Ian Courtney and Jeff Dawn's lab did a lot of pioneering work on the lithium tin system at room temperature. And at 400 degrees C, you can see when you lithiate silicon, you get this kind of slopey region here, but then after that, it turns into a horizontal plateau. And the reason is because you're in a two-phase region, and from the Gibbs phase rule, if we're a two-component system and we're holding temperature and pressure constant, then we don't have any more degrees of freedom. So as long as we have the two-phase coexistence, the potential can't change, and so it reaches a plateau. So anytime you see a plateau in a two-phase system, a voltage plateau, it's a good indication that you're in a two-phase region. As you continue to lithiate, you enter another two-phase region, and so on and so on, and it pretty much at 400 degrees C follows the equilibrium phase diagram. At 25 degrees Celsius, you can see, yeah, it kind of does too, but things get more smeared out, especially over here when you got a lot of lithium and you're reaching the end of this, the fully lithiated state. You don't get these phases anymore in the phase diagram. And there's two reasons for this. One reason is these things have very large unit cells. So at room temperature, it's hard for these materials to organize themselves in these complicated structures at room temperature. The atoms aren't moving around as easily at 400 degrees Celsius. Plus, you'll notice here, this is a region where you have high melting point. And a high melting point means strong bonds. And again, in order to move elements around with strong bonds at room temperature, that's going to be very difficult. And Vincent Chevrier and I looked over all the lithium metal phases that were formed at room temperature, and we basically found a rule of thumb, which was when the total number of atoms in a unit cell of an intermetallic compound with lithium is greater than 17, and if its melting point exceeds 550 degrees Celsius, you'll never see the phase at room temperature lithiation. It doesn't form. And so we looked at this and verified it was true for every lithium metal binary system.
Is that an and or an or?
And.
And.
Yes.
What if you have greater than 17 atoms in the unit cell and it melts at 300 degrees?
Then you may see the phase.
Okay.
But if both of these are true, then you won't see the phase. Yep.
Yeah, I understand. That's cool.
Another example when you won't see a phase is because of kinetics. So lithium aluminum is an interesting system because according to the phase diagram, you should get almost 70% atomic percent lithium into aluminum. But in reality, room temperature, you only get 50%. You only form the LiAl phase. And that's because these phases have very poor lithium diffusion. So when you lithiate aluminum, you lithiate it and form LiAl, and then when you try to go beyond there, you form a little bit of these phases, and it essentially forms a coating on the outside of the particles that blocks the insertion of more lithium. And you can see a little plateau here from delithiating these surface phases on the particles. So this is another reason why you might not see all the phases in a phase diagram, is kinetic inhibition of forming that phase. An important aspect of getting these materials to work is the volume expansion. So early on, one important thing was, well, silicon is cheap, but expands a lot, and all these materials expand. Does one material maybe expand less than another? And maybe that would make it more attractive. And so at 3M, we plotted all the known intermetallic lithium phases, and this just represents some of them, as the number of lithium you can put in per host metal, and on the y-axis, the volume per host metal. And if you plot in this fashion, you get a linear trend, and the slope of this line represents the volume of an atom of lithium in the alloy. And you could see it's the same for any alloy that you pick. And of course, carbon or graphite is different because it's intercalation. And so you have that mechanism where it's already an open structure and it doesn't need to expand as much as these materials, where they have to break bonds and lithium has to find its own place in the structure. And this represents the slope of that line, and you can see it's about 9 plus or minus a small amount for all these elements. So it really doesn't matter which element you choose, the volume expansion is going to be the same. This does make calculations of volumetric capacity a lot easier, because I know that when I insert one lithium into silicon, it's going to take up 14.8 angstroms cubed. And so that makes calculations easy. And that leads to expressions like this. So K is the slope of that line. And so you can calculate the percent volume expansion of any alloy using this equation, where the rho here is the density of the alloy as it's made before you put it in the cell. C is its specific capacity, and F is Faraday's constant. And for silicon, where K is exactly equal to 9, then you can work out that this expression is, this simple quantity here. So as an example, I put in numbers for silicon, and 0.034 times the density of silicon times its gravimetric capacity gives you 283% volume expansion. And the exact number is 280. So this is a very close approximation. We can look at other metal ions and see how they also insert, into other metals, and they do the same thing as lithium. And again, this is not measured quantities in the cell. This is just how much volume do these ions or atoms take in these alloys versus the amount of charge stored in this case. And this information is just from the ICSD database. That's all it took to make this graph. And you could see for some ions, they have greater volume expansion than lithium because the size of the atoms per charge is bigger. Magnesium is attractive. It got a lot of attention because the size of magnesium is smaller per unit charge than lithium. And so you get less volume expansion per unit charge. And as an example, sodium would alloys, when you're inserting sodium in an alloy, you should expect to have about double the volume expansion as lithium. because the size of the sodium atom in alloys is twice that of lithium. And this slide just illustrates that, yes, even though that graph, that plot on the previous page was just made from the ICSD database, you can insert these other atoms, even doubly charged atoms like or ions like magnesium, into alloys, and you can do it reversibly. So it's possible to do this kind of chemistry with other elements than lithium. So the rest of the talk is going to focus a lot on silicon because, as I alluded to before, this is probably the most important alloying material. But its electrochemistry has only been known for the past maybe 15 years or so. And this plot here from a paper in Jeff Dawn's lab by Alf Wilson and Jeff illustrate what the issue was and why so little was known about these materials. And this is just a conventional PVDF coating, I think, or maybe EPDM back then, I can't remember. And you can see what happens. A conventional coating and a conventional electrolyte, you can lithiate silicon almost to its theoretical capacity, but when you try to delithiate it, you can't take any lithium out. And so before you can learn anything about the electrochemistry of silicon, you have to improve the situation. You can't learn anything from this. And this slide illustrates why you get this kind of behavior in a conventional coating. So here's your coated silicon particles, and here's a copper current collector. And when you insert lithium, this coating is going to expand. And as it expands, of course, you have lots of compressive force inside the coating, and that keeps everything in electrical contact, so that when you're lithiating, this thing's expanding and you can get the full capacity even in a crappy coating. But of course, when you try to delithiate now, all these particles are going to start to shrink, and they're going to pull away from each other, and they'll lose electrical contact. And so as the lithium comes out, they shrink, they become disconnected, and you don't see very much during delithiation. So before really we could have learned about the electrochemistry of silicon, we had to solve this problem. And a lot of the work early on, the solution was just put a lot of carbon black and a lot of binder into the coating with a little silicon. And you could get silicon to cycle decently enough to figure out its electrochemistry. And that's basically what the early papers did. You could get silicon to cycle a lot better, though, if you use a different binder than PVDF, a functionalized binder. So here's a plot of, this is a silicon alloy, a 3M silicon alloy, which is basically a silicon iron alloy. And this is a conventional coating with PVDF. If you heat up PVDF, it gets a little better. This is a CMC binder, and this is polyacrylic acid. And essentially, the more carboxylic acid groups you have, the better cycling you get for these binders. And these carboxylic acid groups can form direct bonds with the surface of silicon, which is typically covered with hydroxide, so hydroxyl groups. And so this can react with a hydroxyl group and form an ester bond with the silicon surface. So essentially, binders that can form chemical bonds directly to the surface of the alloy and also completely cover the alloy surface tend to cycle well. Bonds that or polymers that don't form bonds, like PVDF, and don't coat the alloy surface, typically don't cycle very well. I should say, though, that the interesting thing is if you, for instance, make an alloy coating with phenolic resin as the binder, and then you heat the coating to 600 degrees C and carbonize it, the cycling will be very good. And so you can just carbon coat everything and get good cycling as well. So, you know, the role of having an actual polymer is questionable.
Can I ask a question on that?
Yeah.
So are you saying that after you do this phenolic resin coating, you can use any binder and it's fine, or do you still have to use PAA?
No, you can. So what I'm So let me frame this. I guess if you use, phenolic resin and make a coating with phenolic resin binder and sinter the binder. So you're sintering the coating in the absence of air. So you're carbonizing the phenolic resin.
So right on the electrode support, right on the
Put the
current
whole
collector?
electrode in a furnace. Yeah.
Okay,
Then it'll cycle well.
okay.
You can also do that by lithiating it. So if you have phenolic resin or what's the other one again? Polyimide, and you lithiate it in the cell, the lithiation of phenolic resin or polyimide carbonizes it. The lithium's reacting with all the oxygen and nitrogen in the polymer and leaving carbon. And so the way that phenolic resin and other conjugated polymers work for alloys is that they carbonize on the first lithiation. Of course, that creates a high irreversible capacity, but the resulting cycling is better than LiPAA in general. Whenever you see a paper that has a conductive binder, you should be aware of the irreversible capacity. Every paper that I've seen that talks about conducting polymers for binders for negative electrodes have a huge irreversible capacity, which isn't discussed. And it's obviously caused by the expensive conducting polymer carbonizing during the first lithiation, which is kind of humorous in my mind.
That's very humorous, but when you mean carbonize, I mean, what do you really believe is happening? Do you believe you're actually getting a conducting network of carbon? Is there that much reactive elements in those polymers, of that much oxygen to take away and really leave that much carbon behind?
the first lithiation corresponds, so polyimide corresponds to exactly the capacity you would expect for forming Li2O, Li3N, and lithiated disordered carbon. And then the voltage curve of the polymer that's left afterwards looks exactly like disordered carbon.
Okay, that's
And
incredible.
the way you test that out, it's not easy to do that because electrochemists have measured the electrochemistry of polyimide for a long time. And they did that by spin coating to get a thin film. These binders are about 20 angstroms, 14 to 20 angstroms average thickness on the particles. If they're too thick, then your diffusion is bad. If they're too thin, you get holes. So a good target is 15 to 20 angstroms thick. You can't do that by spin coating. So if you want to measure the electrochemistry of a binder, you have to take a inert material like titanium nitride and coat it like a regular coating with the binder. And then all the electrochemistry is this 15 to 20 angstrom thick layer on the inert particles. And then you can see the voltage curve of polyimide and that it is indeed decomposing to disordered carbon.
I remember all this now that you've reminded me, and it's a great story for everybody else to listen to. It's really kind of cool. And I think your message about the papers not necessarily pointing out the large irreversible capacity of conducting polymer binders is a very important thing to recognize.
Yeah. Don't believe everything you read, I guess. The other important component to making alloy material cycle well is electrolyte. These things are electrolyte additives. The alloy is expanding and contracting and disrupting the SEI constantly because of this. And some additives can improve cycling a lot. And one of the most well known is FEC. And here's one of the first papers about FEC. And you could see this is the percent capacity retention without FEC and with FEC, and it makes quite a big difference also to the Coulombic efficiency.
Hi, Mark.
Yeah.
Can I ask a question about the FEC additive?
Yeah.
So for this FEC additive, do they consume during the cycling, or they just form the SEI layers? Are there some NMR or work on this electrolyte to?
It's continuously being consumed.
Okay.
The whole electrolyte's continuously being consumed, and the whole coating thickness continuously grows during cycling. And I'll show that on the next slide. So this is measurements done by Vincent Chevrier at 3M Company, and this shows you the what happens when these materials react with electrolyte as a function of electrolyte additive and as a function of alloy composition. So here we have on the top 12 micron thick coating of 3M alloy, so a silicon iron-based alloy, and below it is pure silicon, also coated with the same thickness, and they look pretty much identical when they're freshly coated. After 100 cycles, you could see that both have gained thickness, but the silicon has expanded enormously, and you can't see any of the original particles. The funny thing is the voltage curve hasn't changed. The silicon is still there, it's just disintegrated into very tiny particles, now covered with SEI. The same thing is happening with the alloy also, but at a much slower rate. And that's either because of its composition, or a combination of its composition, I should say, and its lower volume expansion than pure silicon. This has always baffled me because there's so many papers about how important it is for the binder to cover the surface of all these particles. Look at this thing now. I mean, obviously the binder is not covering the surface of all these tiny particles, and yet it's still cycling. And the same thing goes with the additives. You know, what is going on in this cell? And I don't think that is, especially, it's mostly with respect to binders. I don't think anybody has addressed this issue. Whenever you see a binder paper, they're always talking about the mechanical integrity of the binder and how important it is to bind with the surface of the particle. But if the particle is disintegrating during cycling, why does the binder make a difference? I think that's an unsolved question that probably nobody's really asked.
Let me ask a question there.
Yeah.
You know, you make some really good points here. And have you, in your article you're writing for Kongshu, are you writing these kind of questions down into this paper? Yeah,
but unfortunately, I wrote it 2 years ago. It took that year long to get published, so it doesn't have our newest results in there, but it makes those arguments. Yeah.
Okay, cool. Is that thing out now?
No, it's not out yet.
Is it possible to get a preprint of it?
I can ask Kongshu.
Okay, cool. Thanks.
Yeah. This is a paper by Larry Krauss and Vincent, and I don't know, Brandt. That's after I left, and Lowell Jensen. But they were looking at this surface erosion, as I call it in our lab and in our publications, how the surface of these alloy materials are eating away during cycling. And these folks measured the surface area of these materials, which is a nice way of measuring this during cycling. And you could see with FEC, the surface area doesn't almost increase at all. If you don't have FEC, then the surface area increases a lot. But still, even with FEC, the surface of the alloy is slowly getting eroded away during cycling. Okay, so those are ways of improving performance of alloys. You want a good binder and a good electrolyte additive, and when you combine those things together, you can get a half-decent voltage curve for silicon. You can see a big improvement compared to the one from the 1990s.
Can I just ask one question before you move on from that previous slide? Yeah. I glanced through your slides the other day or yesterday, and I can't remember if you're going to talk about strategies like, you know, encasing silicon within carbon spheres, like all the things that Yi Hui and and the Silent Nano guys try to do, or whether
No,
that's
no, I
another.
didn't. I was planning to do that, but I didn't. It didn't make it to this presentation. This presentation is just going to be basic stuff. But yeah, I mean, all alloys, even SiO, I'll show, have this problem. SiO also has the same surface erosion issue. And in my opinion, the best way of solving the issue is just encasing the alloy in something like graphite so it never comes in contact with the electrolyte. And then you don't have to worry about this anymore. Because for every material, every alloy material, I think they all have this issue.
Mark, can I also ask a question here on the FEC slide, which was really cool, I found. My first question would be how the surface area is measured here, and the second question is, are there also binder concepts that help, prevent surface area growth or surface erosion of these alloy materials?
For your first question, I don't remember. Here's the reference, so I point in the direction of the paper. I don't remember how they measured the surface area. That's a good question. It would be a difficult measurement, obviously. I don't want to speculate. I have an idea how they did it, but I don't want to guess.
But it's not they opened the cells, or they had several cells running and just opened it and did PET or so of, I don't know, how far that they take out.
I think they did it that way, but anyways, I refer you to the paper.
Okay.
Your question about binders slowing this down is exactly my question. Why do binders slow this down? Because binders do slow this process down. Well, no. What should I restate that. Binders don't slow this process down. If you have a binder, a PVDF binder, the worst binder that you can have, and you do a cross section of the coating, after 100 cycles, the alloy looks perfect because it hasn't been cycled. All the particles are disconnected. We've taken pictures like that before. So a good binder will have particles eroded like this. If you have a bad binder and you see perfect particles, perfect particles means that they probably haven't been cycled and you have a bad binder.
Okay, I can see.
You have to be careful.
Okay, thanks.
So let's just check for time. I think for two, yeah, okay. Why don't you tell me when to stop, Jeff?
Yeah, I'll tell you to stop at 125 when it's time.
Okay. So yeah, when you have everything together, you can get half decent voltage curve. And this is what you get for silicon. So you lithiate silicon, you get something that looks like a plateau, a two-phase region, which is, the phase diagram has a two-phase region here. And then you don't see any of these phases, kind of like tin, high melting point and big unit cells. And then when you delithiate, you see another two-phase region. But when you lithiate again, now you have sloping voltage curve, indicating two single-phase regions. So not only is the equilibrium phase diagram not followed, but the voltage curve is dependent on history. And that could be shown even better here. So if you lithiate silicon, you have a two-phase region, delithiate two-phase region, lithiate again, you have single-phase regions. And if you don't go all the way down to 0 volts, single-phase region again, single-phase regions, but then you go to 0 volts and that two-phase region reappears. So this was quite a challenge to figure out what was going on here. And this is an early paper again. You can see the voltage curve looks pretty crappy. This is improving the cycling of silicon just by adding carbon black. But it was good enough to figure out, pretty much what was going on. And so this is ex situ X-rays. So in scan 1, we stopped the cell here and we took an X-ray, and scan 2 and so on. And scan 1, we see silicon peaks, but then we saw amorphous silicon. And then we saw another phase growing out of the amorphous silicon when we got down to low voltage. And that phase didn't match with any known phase. And so we had to figure out what it was. And the way we figured out what it was we just, okay, let's compare to other silicon alloys, and it matched almost exactly with copper 15 silicon 4, and later we found it matched with lithium 15 germanium 4. This is, again, this 15-4 stoichiometry is the closest packed arrangement of different size spheres. So it occurs quite often in intermetallic compounds, but it hadn't been observed before in the lithium silicon system. This is only formed at room temperature. The interesting thing too is how it's formed, because you could see it's not forming here, and then all of a sudden it pops out. And maybe we'll see that. Yeah, I think we'll see that better later on. Right here, actually. This is later study from Jeff's lab doing in situ experiment now. And you can lithiate the silicon in the two-phase region. So you have silicon peaks and they're going away. The intensity is going down as you're forming amorphous silicon. And then all of a sudden, when you get to about 50 millivolts, bang, you get this lithium 15 silicon 4 phase forming instantly, which is quite surprising. The other thing is this phase hangs around and you can put more lithium in. And, you know, the paper and all publications about this phase say, well, it has some, you know, some solubility for lithium. You can put some extra lithium in here. I don't know if that's true or not, because I don't think there's any room for any more lithium in lithium 15 silicon 4. I tend to think that you first form a phase with some vacancies, and then maybe you can lithiate further and make the 15-4 phase, because really there isn't more room for anything in the 15-4 phase. So I kind of find that hard to believe. But at any rate, there's some composition variation in this phase.
What you're saying is probably right, and as you know, it's very difficult to be absolutely sure of where you are on a capacity axis.
Well, that's exactly right.
Where there's some side reactions going on, right?
Exactly. You're at 4,000. I think that's why every paper I've seen, this paper from Claire Gray, they always do this, and I think it's because of the extra capacity you're getting from electrolyte reaction. So with these results, we can get a picture of how silicon is being lithiated. So you start with crystalline silicon, and you lithiate in a two-phase region. And that means, well, the lithium is coming from the surface, so the second phase of amorphous lithiated silicon is forming on the surface. And it grows at the cost of this crystalline silicon in the core until the whole thing turns to amorphous lithiated silicon. And then when the voltage starts going down to 50 millivolts, it suddenly crystallizes into this 15-4 phase. And of course, this two-phase coexistence is going to cause a lot of stress in the material. This amorphous lithiated silicon has about 200% volume expansion compared to this original silicon phase. So there's enormous stress on this grain boundary. And I wonder, can I get that? Maybe I need to get my pointer away to get this movie to work. Ah, here we go. So this is a TEM picture of a piece of silicon particle being lithiated. And I'll play it again. You can clearly see the core shrinking, and then this phase of lithiated amorphous silicon forms around it, and it just falls apart because of all the stress on the particle. Get my pointer up.
Can you spend a moment just explaining how the experiment was done?
Yeah, this is a TEM image, and this is a piece of lithium metal that they just put in contact with the particle. I don't think, does that sufficiently explain it?
That's fine for me. I don't know if others are happy with that.
Yeah, so if you put lithium into contact with silicon, then it'll spontaneously alloy. So during delithiation, the 15-4 phase delithiates in a two-phase region with amorphous lithiated silicon, just as you would guess from the voltage curve. That was verified again by in situ X-ray diffraction. So during delithiation, you form another two-phase region. Again, you get these huge stresses inside the particle, and eventually you form amorphous silicon. Then when you have amorphous silicon does not lithiate like crystalline silicon did. It lithiates in a single phase region. And a nice paper by Jeff used Mossbauer spectroscopy to figure out, they doped silicon with some tin to figure out what the bonding environment was around the host atoms. And this first single phase region was associated with lithium lithiating the silicon, bonding with the silicon phase, so you're forming lithium silicon bonds. But then eventually you run out of silicon that is able to bond with lithium. And so the lithium is forced to go in places where it only has lithium neighbors. And that occurs at much lower potential. It's more difficult to do. And that's why you get this second plateau. But these are single phase regions. So this particle is being uniformly lithiated. There's no two phase coexistence here. So much less stress inside the particle. And so this is probably a good slide to end today. This is a complete picture of the electrochemistry of silicon. So at about 170 millivolts, crystalline silicon is lithiated in a two-phase region. If you go below 50 millivolts, well, the two-phase region is between crystalline silicon and lithiated amorphous silicon. If you go below 50 millivolts, the amorphous lithiated silicon crystallizes to the 15-4 phase. The delithiation of 15-4 phase happens in a two-phase region, again producing amorphous lithiated silicon, and eventually producing amorphous silicon when it's fully delithiated. When you lithiate amorphous silicon, it's in a single-phase region, and if you stay above 50 millivolts where this phase forms, you can cycle silicon in a completely single-phase region. If you go below 50 millivolts, the 15-4 phase will form, and the plateau, which I covered up again here with this label, shows up again. And so this explains this history-dependent voltage curve of silicon, which I think is pretty unique among lithium battery materials. I really don't know anything like it.
Okay, like you say, that's a good place to stop. And, you know, this people really should realize that this took a lot of time to work out in detail. And, you know, Mark's work has been really integral in figuring this thing out, and really very impressive work. Anyway, I have a call at 1:30, so I'm going to leave, but I suspect, as in the usual way, there could be questions for the lecturer that take place after the cutoff time. So I encourage people to ask Mark questions in the next few minutes or so while I go and talk about Canadian neutron scattering facilities, blah, blah, blah. So thank you, Mark. We'll see you again Friday to finish this off, right?
All right. See you then. Thanks, Jeff.
Okay. Hopefully there'll be questions for you.
I'm fine either way.
Yeah, Mark, I had a question if I can. That's a really cool study, you know, with all these features in the voltage curve and how to figure that out. I think that really must have taken quite some time. I had a question about the kinetics, you know, on those two different plateaus. When we first do the lithium silicon filling and then the lithium filling, is the kinetics different for those two regions? I'm asking kind of in the context of fast charging in silicon. Maybe you can also talk about that. Like, is there maybe more opportunity for fast charging, you know, since the voltage is higher than graphite voltage?
The kinetics is pretty crappy. I don't know if there's been a good study. I don't know of any study that has compared the two-phase region to the single-phase region off the top of my head. I've never seen one. A lot of work has been done looking at the kinetics of the single-phase region, and it is true hysteresis, the difference between charge and discharge. No matter how slow you go, you will always get a large difference between charge and discharge of silicon. And the reason there's hysteresis there is because you're breaking and reforming bonds. And whenever you do that, you see hysteresis. So the kinetics is not as good as graphite, but it depends. You know, you can make silicon, again, very small and embed it into graphite particles. And then the kinetics are fine. So you can help that out with morphology. So it's
Okay.
difficult to compare kinetics of materials, under what basis, the same size particle or same capacity normalized, but then you have to worry about the particle size. I don't know.
Yeah, true. Okay, thanks.
Yeah.
Hi, Mark. So I've read that lithiated silicon is more closely packed in terms of its unit cell or its density, for especially the Li15 Si4 version compared to just metallic lithium on its own. And that's always been counterintuitive for me. So could you maybe explain why that's the case or how that can happen, that we can have more densely packed lithium?
Well, you can form, I expect in lithium fluoride, the lithium is far more densely packed than in lithium metal, just because the lithium fluoride bond is so strong. It's pulling all the ions together. So as you go above 0 volts, that represents an increase in bond strength to lithium, and that means tighter packing. So it would be interesting, maybe as an exercise, look at something like lithium cobalt oxide. I wonder what the packing of lithium is in that versus lithium metal. I don't know. That would be interesting to see. It might be greater for lithium cobalt oxide than lithium metal too.
I see. Okay, thank you. So it's just about bond electronegativity and bond lengths on. Okay.
Well, yeah, and also you can even consider these things as spheres, and as you go higher in potential, it means you're taking away more electrons from lithium and essentially making, going from an atom, which is big, to an ion, which is small. And as you go up in potential, you're going everywhere in between. So you can think of it as packing of spheres, if you wish also.
Thank you.
Yeah.
Hi, Mark. I got 2 questions, but I'll start with one that you just mentioned earlier about the hysteresis of the alloy.
Yeah.
So what is the, I guess if you go super slow, you'll find like what the true hysteresis is, but what is the, I guess, max hysteresis, or sorry, minimum hysteresis or max energy efficiency of that? And is that similar to the other alloys, like with tin or other materials?
Some alloys are very fast. It depends, and within some alloys, like you saw the lithium aluminum system, you got half decent cycling in one region, and the other was so poor kinetics you can't put lithium in there at all. So within the same alloy system, you could see differences in hysteresis as you go from one two-phase region to another. I'm trying to think of the smallest hysteresis. There was a nice study by Lawrence, was it? No, I think it was Berkeley, group at Berkeley did a study where they measured essentially the open circuit voltage of lithium and silicon. I think their dwell time was sort of like 2 days at each voltage point, at each composition, going up the voltage curve and back down again. So very, about as open circuit voltage as you can get. And it was like, what was the difference between the two? I can't remember. It was I don't know. I'd have to guess 0.1 volt, something like that. I have to look back at the paper. It closed up, but it never closed up completely. It never looked as good as graphite or the cathode. I don't have the number on top of my head, though.
Okay, thanks. And then the second question was, so we know when there's a two-phase region that it's a voltage plateau.
Yeah.
But when as you're lithiating the silicon, the amorphous kind of goes crystalline once it goes to lithium-15 silicon 4. Does that just happen for all of that immediately? Because there's no voltage plateau when you look at the voltage curve.
Exactly. It spontaneously crystallizes the whole thing at once.
Oh, wow. Okay. Thanks.
Any other questions? No? Well, in that case, maybe you can, if you have think of anything else, you can ask me on Friday. And yeah, I'll see you folks Friday, and yeah, I think we'll finish this up. We're about halfway through. Doing well. Okay, so I'll see you guys in a couple days. Bye.
Thanks. Bye.
Thanks.
Thank you.
Thank you.